Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to welcome Ari Gerfinkel from the University of Toronto, who is visiting the next 2 days, and he's worked on software model checking, something near and dear to many of our hearts, and he's going to tell us about his thesis work on construction analysis and understanding of software models.
Thank you. Hello. So the main focus of my research has been on developing techniques to help software engineers build more reliable and dependable software systems. And I believe that we can do it by giving software engineers better tools that give them more confidence than testing alone, while remaining easy to use. So I think that these tools should be fully automatic. They should be reasonably easy to use, so that existing software engineers can apply them effectively. They should come with some kind of guarantees, and hopefully some guarantees that we can measure, and come with guidelines and methodologies to apply them effectively. And finally, they should be applicable to real software systems, because that's where they needed the most. So during my studies at the University of Toronto, I worked at a variety of projects in this general area of automated reasoning. Some of the projects, like this multivariate model checking, are more exploratory in nature. And the idea was there to try and look how we can extend the analysis to earlier stages of the design process, where we have to deal with partial information and potentially even inconsistent information about the system we're building. Some other projects, like understanding counterexamples and vacuity detection, deal more with the usability issues surrounding automated analysis. So in understanding counterexamples, we looked at giving user a better support to understand the result of a model checker and understand the counterexamples that are generated. And in vacuity detection, we looked at how can we improve the trust in automated analysis, and in particular in checking whether every part of a formula is relevant for the particular analysis. Otherwise, the formula is satisfied vacuously, which probably indicates some kind of a modeling problem. And in the temporal logic query checking project, I looked at how can we use the same model checking technology to try and discover properties of a model instead of check them whether they're satisfied or not. And what I'll be talking about today is my latest project, which is software model checking, which basically tries to apply model checking techniques to analysis of software programs. So let me start with just a quick overview of what a finite state model checking is. Basically, we start with some software hardware artifact and a correctness property, and we want to know whether the artifact is correct with respect to this property. We need to extract the finite state model of the artifact, translate the correctness property into temporal logic. This two are then given to a model checker, which automatically decides whether the artifact is correct or not, outputs yes or no, and if the answer is no, it can potentially produce a counterexample. So what we want to do is we want to apply this model checker to software programs. And of course, the problem is that programs are not finite state. They use integer variables, recursion, unbounded data structures, and all of these features, which makes them infinite state and really hard to analyze. So we can't just take a program, feed it into a model checker, and expect to get an answer. So what we need is some kind of an abstraction. We need to somehow reduce a program into a finite model, which is small enough to analyze, but still rich enough to give conclusive results. Now, of course, this doesn't solve any problem yet, because we now have two problems. We need to know how to check the abstraction, but we also need to know how to construct it, and this is not a trivial task. And the idea is that we can try and build this abstraction iteratively in what is known as a counterexample guided abstraction refinement framework, or CEGAR for short. So the way this framework works is we start with a program and a safety property trying to check whether some error state of a program is unreachable. We build an initial abstraction of the program. We over-approximate it by a Boolean model that the model checker can understand, and then use the model checker to check our property. If the result is yes, then we know that error is unreachable in the Boolean model, and since it's an over-approximation, it's unreachable in the program, and so we can stop. Otherwise, if the answer is no, we get an abstract counterexample, which is an execution of this Boolean model that leads to an error state. We can then check whether it corresponds to an execution of a concrete program by simulating it over the program and trying to see if it's a valid execution. If that works, well, we just found an erroneous execution, and we can report it to the user. Otherwise, there was some reason why we have an execution in this abstract model, which is not part of execution of a program. And we can use this information to refine our abstraction and then repeat this process again. So just to give you a quick example of how it works. So here we have a program, and we want to know whether error is reachable. The first step is we build our abstraction, which initially just contains the control flow statements of the program with everything else abstracted away. So in particular, the star here indicates that the condition of the while loop is abstracted away and no longer known. We then build a Boolean over-approximation of this, which in this case is just a control flow graph of the program, and check whether line 5 corresponds to the error statement is reachable or not. Now here, it's easy to see that it's reachable, and the model checker will produce this counterexample showing how. We're now going back to our program and try and see whether this counterexample is also a feasible execution of the concrete program. So the first step is perfectly fine. We can go from 1 to 2. Now the second step is a little bit problematic. So according to this counterexample, to get to an error, we have to go from line 2 to line 4, which means we need to skip this while loop. But if we look at what happens in the program, after we do the first line, y is equals to 2, and therefore we have to enter the while loop. But according to our counterexample, we have to skip it, which is not possible. And the reason why we have this execution in our abstract model is because it doesn't keep track of the condition of the while loop. So this is what we need to do in order to refine abstraction. We need to add this condition into our abstract program. So we now go and repeat this process again. And this time, the abstraction that we get also has a control flow statement, but it also has a Boolean variable b that keeps track of this condition that we want, whether y is less than or equal than 2. And for every statement, we have to figure out what does the statement do to this condition. So the first statement sets it to true. The while loop condition just depends on it. This statement basically says that if y was less than 2 before we subtract 1, then it remains less than 2 after. But if y was not less than 2 before we subtract 1, then we don't know what happens to it after, which is indicated here by the star. And there's nothing that we can say about this condition, so it remains unknown. And that's it. So again, we build our over-approximation. And now here, it's very easy to see that the line 5 that corresponds to an error is unreachable. And basically, what we can see from this over-approximation is that the only way to get to an error is if we ever get to line 2 that corresponds to the beginning of the while loop, with the loop condition being false. But according to our abstraction, initially, the loop condition is true, and then it remains true within the loop, and therefore we never get to the error state. So now let's go back and try and look again at what was going on. So we had this abstraction, which is inherently a partial model. It describes some of the information that we know about the program, and it hides some of the other information. So in particular, this star here means that the condition is unknown. It's been abstracted away, and we no longer know what it is. And if we look at the model that we use in model checking, well, it's an over-approximation in the sense that the same condition, the one that corresponds to line 2, is modeled as a non-deterministic choice, which basically says we assume that either we enter the loop at this point or we exit the loop. So this means that this model has strictly more behaviors than our abstract program. And therefore, if we prove that something is unreachable in this model, it's really unreachable. But if we prove that something is reachable, well, that doesn't actually mean anything. So this poses an interesting limitation to the CEGAR framework. So first of all, because we over-approximate, if the model checker says yes, well, we can trust this result. But the model checker is biased to trying to prove that something is unreachable because it only sees an over-approximated model. If the answer is no, well, then we need to validate this answer. We can't trust it. And in order to do this, we need a counterexample, which is linear, so that we could simulate it, and finite, so that the simulation stops. And that means that this whole framework is limited to safety properties, because this is the only properties that have finite and linear counterexample. And all of this problem is caused by the fact that we're using a normal model checker, and we try to over-approximate our abstract models in order to do so. So let me just show a few examples of how over-approximation causes us to do more refinements than strictly necessary to solve the problem. So here's a simple program. And just by looking at it, it's easy to see that error is in fact reachable. Here's its abstraction. This abstraction doesn't even have any predicates, but it's still enough to show that, well, yeah, error is still reachable. And this is the corresponding over-approximation, where instead of saying that this condition is unknown, we treat it as a non-deterministic choice. And on this over-approximation, the only thing we can say is that, well, error is possibly reachable. We're not sure. We need a counterexample to validate. So star means that the condition is unknown. Non-det means there is a means that there's some non-deterministic choice controlled by something outside of the program. So star would correspond to an internal non-determinate, and non-det would correspond to external non-determinate. Well, here, it's not referring to here. Yeah, it's referring to, can we, using this, conclude that error is reachable in here? Well, it's possible because it's an over-approximation, and whenever we detect that error is reachable in an over-approximation, we have to say possibly we need to do more reasoning. Now, in this case, you can eyeball it and say, there's a simple reason. Well, in the second column is because there's enough information here to say that error is definitely reachable. Because here, when I analyze this program, that's not an over-approximation, that's an abstraction. So from it, I can conclude that error is reachable. So an abstraction is something that describes some of the information that we know about the program and doesn't describe some other information. So here, this is an abstraction. It tells me exactly what I know about the program. I know its control flow graph. I know that this condition is something. I just don't know what exactly it is.
Are you going to define abstraction?
No. But I'm gonna give more examples. So when I say abstraction, I mean a Boolean program with stars in it, where star means it's an unknown condition.
But generally, I guess the difficulty when I think of the star is I think of it as being essentially an abstraction of x less than 0, because I'm losing information. So the abstraction has more possible executions in the program because that predicate.
Well, in an abstraction, you can say whether an execution depends on something that you abstracted to or not. So here I can say that when you go from 1 to 2, that's a concrete execution of the program.
Right.
It doesn't depend on anything that I've abstracted away. Whether I go from 1 to 2 to 3, well, that depends on star, because the only way I can get to 3 is a star has to be true. So it depends on information that I've removed, so I cannot say conclusively. Whereas here, because you have this non-determinism, you can't tell. You don't know whether this non-determinism is an external one or an internal one. There's going to be next example right after. But if you just follow the standard approach where you say, I have an over-approximation, I check whether error is reachable, the answer is yes, it's reachable. You can't yet trust it, you need a counterexample to validate. So the counterexample that you can get could be this one. That's a perfectly valid counterexample. But this counterexample is not a feasible counter execution of this program. which means if you get this counterexample, you'll need to go and do an additional refinement step, add more predicates. Also, there is enough information in this abstraction to conclude that error is reachable. But here, well, you're going to get a counterexample. You should get a counterexample, which will tell you you go from 1 to somewhere in here, not sure where, and then definitely to 6. So you don't get a complete counterexample, but you get enough information to prove that error is reachable. So here's another example. So here, now this concrete program also has this non-deterministic choices, which would be used to model a choice that depends on maybe a user input, or a choice that depends on some external resources which we don't want to model. And so if we look at this program, it's clear that error is reachable in it. Right? If we build its abstraction, well, when we abstract, we can still keep the fact that there's a non-deterministic choice here and here, and this condition is now abstracted away if we don't have that predicate. But there's still enough information here to prove that error is reachable.
Which error?
Don't know. One of them. You can think of this error label as calling an error function. So we're checking whether an error function can be called. So I don't know which one, but I know that, well, this is an external choice. So it means whenever I execute the program, a user can input something to force the program into here. And then either this condition is true and I'll get to an error, or it's false, and then something can, again, force the program to get to an error state. So any way you look at it, the error is reachable. If we build an over-approximation, well, now we can tell the difference between a non-deterministic choice, which is really an external choice, and a non-deterministic choice, which is part of our over-approximation. And again, is an error reachable here? Well, possibly. We need a counterexample in order to validate. We get the shortest counterexample, which is typically what we get from a model checker. And this particular execution is, again, not a feasible execution of this program, which means this will cause us to add more predicates to try to refine our abstraction to remove this counterexample. Yes. Mm-hmm. Yes. So the definition that, at least intuitively, the definition of what does error reachable means in here is error is reachable in here if for all concrete programs that could have been abstracted to this one, error is reachable. You can. So no matter how star actually is resolved by the program, no matter what condition it is, error is still reachable.
I see. So it's like a there exists on the non-dev.
Yeah.
For all stuff.
Yeah. So there exists a sequence of choices the user can make, so that from the abstraction we can conclude the program will get to an error state.
So now, if you want to connect this to mode transition, the star corresponds to for all, and the non-dev is you have some notion of that non-dev.
Non-dev would mean.
Is angelic. No.
Non-dev is the demonic.
Well, it depends on.
It depends how you point it. But one is angelic, one is demonic. One is internal, one is external.
Always choose the right way to get to an error. Right. So if the angel is help, I want to get to an error, so the angel helps me get there. Sorry. Okay. So right, fine. So fine. So non-dev is demonic, and because it always makes a choice to get closer to an error, and star is angelic.
It doesn't matter how you. The opposite. except I'm looking at it from a point of view whether error is reachable. Right, and you're looking at it from the point of view of whether a program is correct. So when I say yes, it means the program is actually not correct because error is reachable. Then again, it changes the point of view of what angelic is and what demonic. So the program is a refinement of the abstraction. No, the over-approximation would be an abstraction, a refinement of the abstraction. Right? Because you can look at this as, again, as a program that has everything known. It's just some choices are not made by the program, but are made by some external entity. So, for example, it could have been that my program looked like this initially, and this is what it got abstracted. Or a partial path, yeah. Yeah. Or some kind of proof that tells you that there exists. Okay. So the problem that this over-approximation causes is that it causes a loss of information that we have in our abstract programs. It makes the analysis somewhat easier when we want to prove that the property is true, that error is unreachable. But when the property is actually false and error is reachable, and it leads to unnecessary refinements, and it makes it harder to detect bugs, because over-approximation introduces more spurious behavior. But we could have avoided this problem if we would model abstract programs by partial models instead of modeling them by Boolean models, and extend our model checking to such models. And in fact, there have been quite a lot of work on reasoning about partial models, how to represent them and how to analyze them. And basically, there's a number of different modeling formalisms, such as model transition systems, mixed transition systems, three-valued Kripke structures, and so on, that's been proposed to capture a partial model. And then each such thing comes with a partial model checking algorithm that takes a temporal property, not necessarily a safety property, but maybe an arbitrary CTL property, and one of these structures, and can give you one of four possible answers. Either true, indicating that there is enough information in the model to verify the property. False, meaning that there is enough information in the model to refute the property. Unknown, meaning that there is not enough information, the model is too partial to claim either way. And sometimes you can even get an inconsistent answer when there's some kind of inconsistency in your partial model, and you can both prove and disprove a property. Now, this last part is not really relevant for this talk, because here I'll assume that we'll always derive our partial model from a concrete program, which guarantees that this model is always consistent by construction. So in our work, these partial models can actually be related based on how well they capture this partial information. And the basic idea is that in order to represent that the model is partial, we need to have two kinds of transitions: May transitions that indicate what's possible, and mass transitions that indicates what's necessary. If we also have a consistency requirement that every mass transition is a May transition, then we get what's known as model transition systems. And equivalently, we can get exactly the same type of models if we take Kripke structures and extend them to three-valued cleaning logic. If we drop this requirement of consistency, then we get mixed transition systems. And in this logical side of things, that corresponds to taking Kripke structures and extending them to four-valued Belnap logic. If we go further and introduce hypermass transitions, so transitions that go to sets of states, then we get generalized transition systems. And we can go further and even use tree automata to represent this partial system. And each time we go down, we can capture this partiality of a system more precisely. So the systems that we actually use in our work are this Belnap Kripke structures. And the reason is that, on one hand, they support monotonic abstraction refinement. That means whenever you refine this such a Kripke structure, you get something which is strictly more precise, which is not true about model of three-valued Kripke structures. And at the same time, they're fairly easy to analyze, which is not true about this structure. So what is Belnap logic and this Belnap Kripke structures? Well, a Belnap logic is just an extension of Boolean logic of true and false with two additional values. The bottom value that corresponds to unknown, and the top value that corresponds to inconsistent. Now, if we want to compute or reason with this logic, it's convenient to turn it around so that true is at the top and false is at the bottom. And then conjunction and disjunction just correspond to meet and join in this logic. And negation is just an operation that turns it upside down. So for example, true and unknown, according to the rules, would give us unknown. And true or unknown would give us true. So Belnap Kripke structures are just traditional Kripke structures extended to this logic, which means that propositions can take one of these three values, either true, false, or unknown. So here, for example, we have a state where P is true and Q is false, and another state where P is true and Q is unknown. And transitions can also take the values from the logics, where top transition correspond to a necessary behavior, bottom transition correspond to a possible behavior, true transitions correspond to something which is both necessary and possible, and false transitions correspond to impossible behaviors, and they're not shown in the structure. So the easiest way to understand, to try and get an intuition to what the structure means, is to look to what Boolean structures it corresponds to. And it corresponds to a Boolean structure which has at least all of the necessary transitions, which are these two, and at most all of the possible transitions. So this Belnap Kripke structure represents the set of Boolean Kripke structures that lie between this one and this one. So that's in what sense it represents partial information. It represents one of the structures, but we don't know which one. And when we reason about this structure, it's like reasoning about all of these things at the same time. So possible. That's a necessary. Yeah, that's like a must. That's like a may. And that's like a true, which is must and may. Because we do not require that every must is a may, since that leads to being able to represent information more precisely. So you have three choices: may, must, and may and must.
So I'm trying to understand the operation. If I'm at that state with the solve case.
Okay. So this kind of means we're representing something that has a non-deterministic choice between setting P to false and Q to false, or setting P to true. And if you happen to take this step that sets P to true, then we do not know whether Q will be true or false. So what's known? A non-deterministic choice between setting P to false and Q to false, or setting P to true and something happens to Q. And what's unknown is when we pick this choice, what will happen to Q, whether it will be true or false. That would mean there is a non-deterministic choice. That means it's an external choice that somebody else makes. That you have two actions and you have a non-deterministic choice between them, and the choice is made not by the program but by some external entity. Well, I'm slightly abusing notation here. So here I have the state where P is true, and there's no value for Q. So really I'd have to represent this using two systems. One where P is true and Q is true, and one where P is true and Q is false, and say that what is necessary is that it's one of these things. Not in this. This is a Boolean model. But the least information is that P has to become true. And I don't know what happens to Q. And this is the possible choices. Q could become true, Q could become false. So there's relation between states. And so you can't just match transition by transition. Yeah. So the mass transition tells us what's necessary. The green transition tells us what's possible. If we start randomly changing things, we may create a system that says it's necessary for P to become true, and it's not possible for P to become true. Right? Because if we say remove this green transition, then it's like saying it's not possible for P to become true. Because the set of our possible next state does not include a state where P is true. So if we're just trying to represent something by its over and under approximation, we can potentially create something which has an empty intersection, so an inconsistent system. Now this won't happen in this case because we're going to start with a concrete program and derive its partial representation, so we, by construction, guaranteed that the result is consistent. Mm-hmm. And that they are connected together to represent that it's necessary that one of them is taken. Right? Because possible also means that possibly none of them are here. This necessary ensures that one of them is taken. So another way to look at it, if you want to use hyper transitions, you'd say this blue transition really corresponds to a hyper mass transition to this set. False. Unknown. Inconsistent. Inconsistent. Okay. So this is what is called a Belnap Logic, and this is the information ordering. So as you go up, you have more and more information. So you have true and false that have the same amount of information and are incomparable. If you know true, you know true. If you know false, you know false. All you can know. Bottom means lack of information. That's why it's at the bottom here. And top means that you know both true and false. It's information overload. But when I want to reason about it, if I want to know what does and mean, actually, if we just turn it this way, then we can take meet and join of the lattice as our ands and ors, and they will correspond to our intuitive notion of what they should be. Right? Like a true or unknown, well, that should be true. Or if we do false or unknown, well, that should be unknown, and so on. And this is known as the truth order of the lattice. So this is how to, it's computational order when we want to compute operations. And this is its information order when we want to know how much information we have. What does precision of the abstraction mean? Do we have the most definite value, or do we not? Or do we have an inconsistent result? So the nice thing about this Belnap Kripke structures is that they're very easy to check temporal properties over them. And in particular, we keep semantics of all of the temporal operators as usual, but we interpret all of the propositional connectives in Belnap Logic. So for example, the semantics of EXP remains the same. It basically says it's a disjunction over all states of the value of a transition to that state and the value of P in that state. But now, conjunction and disjunction are interpreted in this Belnap logic. So, for example, if we'll check here in this state, what's the value of exq, state is 0, we're going to get that the result is unknown. And that's because the only place where we can get to a state where q is through an unknown transition. And we can do the same for other other properties. And actually, the work that I've done on multivariate model checking is in part implementation of this idea in a model checker which we call KiteCheck. So what this talk is about a different model checker called YASM, that stands for yet another software model checker, whose goal is to try and combine the CEGAR framework with KiteCheck's ability to reason about these partial models. And so basically we want to get a framework that looks kind of like the normal CEGAR framework. We want to keep the same notion of abstraction because abstract programs already have this partial information. We need to give them semantics so that we can translate them into Belnap Kripke structures. We would then be able to take an arbitrary temporal property and use KiteCheck to check whether it's true or false. If it's either true or false, well, then we can stop. Otherwise, we'll get that the result is unknown, and we'll need to do something to be able to refine our abstraction and for this process to continue. So before I'll talk about this, I want to show you just a quick demo of the tool on the example that I showed you before. So here's first example. So this is the program that we saw before, where we have this if statement that doesn't actually do anything, and we get to an error state. And so what we expect, if we check whether error is reachable, we should be able to do it without needing any predicate. And so to do this, we run YASM, and this is our property, whether an error state is reachable on this program. And after a little bit, it comes back with saying, well, the property that you checked is true, and I didn't need any predicates to do. So this is just a very simple example. Here's a more interesting one. So here we have a program that has some non-deterministic choices, also makes some computation with x and y, which looks fairly complicated, and we want to know whether it can reach an error label, so whether it can call the error function.
This program doesn't have not.
This is a concrete program. A concrete program can never have start.
Why is that? Because it not work out.
It does. It just then it will not be a concrete program because it would be an abstraction of something. That's why you have start. So non-dat would correspond to some external choice that may be instead. Yeah. Yes. So if we look at this program, it may look somewhat complicated because of all of these things. But actually, we can check, we can prove that error is reachable without needing any predicates at all, just from the control flow structure of this. So again, if we run YASM on this example, quickly comes back and says, yep, error is reachable, the result is true, no predicates needed. It does, but note that you can look at that. But the basic reasoning, if you look through it, well, you can make this choice. You can always force the program to get to an error state using non-deterministic choices, no matter how this other conditions are abstracted away. You can always. Abstract counterexample could be a tree or partial explanation, and then you would need to simulate it over the program to get the concrete. A concrete counterexample, because you're interested in an execution of the concrete program anyways that gets to an error, and in the concrete program it has to be a trace.
Are you guaranteed that you pass the tree will lead to error?
Yes, that's what you're looking for.
You
can take any one of those paths, and then you may pick an invisible one. And so instead, you could try and run your feasibility analysis, but restrict it to that trace. So here's just one more example. Here's a program that has some kind of while loop with some non-determinism in it. And, well, one of the things we can do is we can check whether this program terminates, which is not really interesting because basically it says, well, I need to know that you enter a loop and actually the loop can terminate in one step. So that's a proof that tells us that there exists a terminating execution. But what's more interesting is we can also check whether it's possible for this program to not terminate, whether this loop has non-terminating execution. And we do it by asking whether there exists an infinite execution that never gets to the last program statement. And again, if we run it, we get that, yeah, that's true. The only thing that we needed to know is whether the loop condition is true. And basically, the explanation here would go as, well, you can get inside this loop, and then you can always pick this branch of an if, increment y, and always stay in that loop. And this is an example of a property which is not a safety property. It doesn't have a finite linear counter. So what I'm going to do in the rest of the talk is show how we go from these abstract programs to Belnap Kripke structures. Talk about how we do abstraction refinement in this case, how this new framework can be exploited, show some experimental results, then conclude and talk about future work. So in order to interpret this abstract statements, we need to give them some kind of transition system semantics. And the typical view is to do an over-approximating semantic. So here we'll start with some statement. Here's its abstraction using two predicates. And to get an over-approximation, intuitively we have to treat the star as a non-deterministic choice and just build a transition system corresponding to the statement. So in particular here we have this non-deterministic choice, which basically says that when B1 is false and we run with as a statement, we don't know whether B1 will be true or whether it will be false. So that's our over-approximating semantics of the statement, so part of it.
So y is greater than 2 and subtract 1.
Then we don't know. And we model it by saying star means non-deterministically true and false, which gives us a Boolean system where. But we can also build an under-approximating semantics from the same abstraction. And intuitively what we would do here is we treat star as just an extra value that we have that we can assign to a variable and just propagate it throughout our program and make sure we never make any decisions that depend on that value. So what we'll get here in the same state, well, when B1 is false and B2 is true and we run this statement, well, B1 is going to get star, but B2 is going to remain unchanged, it's going to remain true. If we happen to run the statement in a state where we didn't even know what the value of predicate B1 is, well, we would just stay in the same place because B2 would still remain true and B1 would still remain star. So this would be our under-approximating semantics corresponding to this abstract state. It refines the abstract program and is independent of the concrete program. So I was using this internal and external non-determinism just as an intuition, because I need. Yes. I don't know. Maybe. Not. So that's one of the connections which I haven't explored yet. But in some sense, so you want to say that you do with ATL. You could say one agent controls one set of choices, another agent controls the other set of choices, and then you want to know whether one can force, which would be very similar. Now, what's the exact connection, whether they're exactly the same or there's some difference in terms of what you can prove and what you cannot prove? What's the complexity of proving it? That I don't know. The thing doing it for ATL would be more precise but also more complex.
So really what you're doing is Boolean programs in traditional sense. There really isn't a star thing. There really isn't.
Yes. Which doesn't have any logical meaning. It's just star. Right, then which we just propagate around in our program and make sure no condition depends on it. That means any execution that I have in here can be necessarily mimicked by an execution in the abstraction and can be mimicked by an execution in the concrete program. Because under approximation, none of the steps will depend on steps. But because we introduce stars in here, I may not be able to give you an exact execution. I may not tell you what the value of this predicate is. I'll tell you that there exists an execution where you get to the state and the predicate will have some value, and then the rest of the execution does not depend on it for a bit, and then maybe it gets a value, and then we continue. But you would need to track them somehow. And what we're doing is we're effectively tracking them by interpreting everything in this Belnap logic. So you tag transitions with logical values, and that in effect is the same as tracking things like. It probably would be the same as. So in fact, the implementation that we do, we reduce everything to Boolean systems and use Boolean logic to do all of the underlying reasoning. So in fact, that may be, if you ignore how we got there and just look at it. So I hope I've convinced you that we can interpret this in an over-approximating fashion, which treats star as a non-deterministic choice, anything happens, and in an under-approximating fashion, which basically says star is an extra value, let's see what we can do without depending on it. And what we work is what we call exact semantics, in the sense that they combine this over and under approximation. They neither over nor under, using this Belnap Kripke structures. And the basic idea is that, first of all, instead of star, we're going to use our value bottom that represents a known. And then for transitions, we're going to say transition is possible if it only appears in the over approximation. Transition is necessary if it only appears in the under approximation, and the transition is true if it appears both in over and under approximation. So now this Belnap Kripke structure is an exact representation of this abstract statement in the sense that it has all of the same information that you have inside the statement. He knows that certain things will happen because of this true transition. He knows that certain things are necessary because of some necessary transitions, and certain things are not known, like we don't know when we execute a statement from here what will happen to B1. But we still know that B2 is unchanged, so we still have that information here. you try and the transitions that you put should not depend on start.
What if there was an instruction in the program code?
Well, then you could not. Then you would not be able to say whether this transition happens or doesn't happen. For example, say you have if star and you have two branches. Now you don't know what the star is. Star could have been a constant, could have been true. Then only one branch would really happen. Or it could have been false, and so that only the other branch could have happened. And so in an under-approximation, you just say, I reach a state where I have lost all information.
Right, and that would be precisely where the green arrows come.
Yes. And you typically look for this kind of case, where green arrows tell you there's some split, but blue arrows still tell you, and something is still known for sure. So if we apply this to every statement in the program, we get a Belnap Kripke structure that corresponds to the full program. So here how it looks like for this example that we saw before. And again, the key thing here is to know that this Belnap Kripke structure represents exactly all of the information we have in this abstraction. So this non-deterministic choice here is modeled by a non-deterministic choice between two true transitions. The program can non-deterministically go here or here. And this unknown condition is modeled by a non-deterministic choice between two unknown transitions, meaning that, well, here it's possible that the program goes this way, it's possible that it goes this way, we just don't know which way it will go. Whereas here, it's the user input decides which way it will go. So we have all of the information from this abstraction in the model that we're going to analyze. So this gives us sort of this abstract model checker that takes a program, a temporal property, abstracts the program somehow, converts it to a Belnap Kripke structure, and now can check and see whether there's enough information to either verify or refute the property. And if there isn't enough information, it will say that the result is unknown, and we need to do refinement. So if we look at just safety properties, then we can actually do exactly the same CounterExample guided refinement. Since if we know that whether error is reachable is not known, then we're going to get a CounterExample. We're going to get an execution that goes through all of these transitions, gets to an error state, and has at least one unknown transition. Basically saying, if this transition is true, then we would get to an error. If this is false, then we don't get to an error. So that's why we don't know what the actual result is. Now we can ignore all of these transitions, whatever their values is, and just look at it as a sequence of states. That's just a counterexample, so we can apply any of the standard counterexample guided refinement techniques. But this would only work for safety properties. Now the interesting thing about ChaiCheck is that in addition to giving you an answer, it can also produce a proof explaining how it got to this answer. So for the same example, the proof would look something like this, where you would read it bottom up. Basically, this last line says that we don't know whether error is reachable from this initial state, and then it tries and provide you an explanation what's the reasoning the model checker went through. And basically, here it says, well, in 4 steps, I can show you that whether error is reachable is unknown. And that's because there is a true transition from S0 to S1. And then whether error is reachable from S1 is still not known. And then there is an unknown transition from S1 to S2. It gets us here. And then we know that from S2, error is reachable. Now, just by following this proof, we know that, well, right away we can stop following the proof at this point, because we only care why the result is unknown. We don't care why we can actually get to an error from a certain point. And now if we look at this part that we actually used in the proof, we'll see that the only reason why whether error is reachable is unknown is because we had to use some unknown transition. So that's the cause why the result is unknown. We can map it back to our model, figure out what statement it corresponds in an abstract program, what statement it corresponds in a concrete program, and apply refinement to try and find out more predicates to turn this unknown transition into either true or false. So when we use these proofs to guide the refinement, then only a part of a proof has to be generated. There is no need to validate any counterexamples because unknown steps are already explicitly marked with no proof. And since we can generate this proof for arbitrary properties, refinement is no longer limited to finite linear explanations, which is what allows us to do properties other than the safety property. So this is
This is now an alternative to CEGAR.
this is
Earlier on, you talked about CEGAR.
counterexample.
And what we're saying now is we don't need to do this anymore because this is subsumed.
Yes. So if your model checker will tell you, I'm reasoning about this abstract model, and the result is unknown, it can pinpoint you to which facts it needs about the model in order for this proof to be conclusive, and then you just go and refine it. But you could still rely on counterexamples if that happens to be better for certain kind of problems. So one does not preclude another. And so this is an overview of this new framework, which combines CEGAR with reasoning about Belnap Kripke structures. And basically, we use this exact semantics to convert abstract programs to Belnap Kripke structures, take arbitrary temporal property, use chi-check to decide whether it's true and false, and if the result is unknown, generate a proof, and use this proof to find place to refine and generate and improve our abstraction to repeat this process. This is the architecture of the tool, and basically starts by parsing the program, abstracting it by building a control flow graph, and then getting into this loop where we check whether property, we check the property. If the result is definite, we stop. Otherwise, generate a partial proof, mine it for new predicates, and refine. So the tool itself is about 30,000 lines of Java, and it's based on a whole variety of third-party components. In particular, we use SEAL to simplify parsing of C programs. We use CVC Lite as our tier improver to figure out what happens to each predicate in every statement. And chi-check itself is based on Colorado University decision diagram library. So now let me show you a few ways in which this exact semantics can be exploited within the CEGAR framework. So if we look again at how the CEGAR framework operates, we'll see that we constantly create one abstraction of the program, run the analysis on it. If the result is inconclusive, we build a new abstraction which looks very similar to the previous one, and then run the analysis again. And so it seems it would be very useful if we could reuse the analysis that we've done on one abstraction when we construct the more refined one. And this is actually rather easy with exact semantics. So here, this box represents some kind of an abstraction, where this is our initial state, this is our error state, and we want to know whether error is reachable. Since we use a backward symbolic analysis, then when the analysis terminates, we know not just whether error is reachable or not, but we actually can partition this abstract state space into 3 regions. We know that in some states, error is reachable, so these states can actually get to an error. In some states, error is unreachable. And in other states, the result is inconclusive. And of course, this process would continue refining until the initial state belongs to one of these groups. Now, because this is just a collection of abstract states, we can represent it by a formula over the predicate that we used in the abstraction. So maybe this region corresponds to, well, error is reachable if we're already at an error state, or we're at line 10, or we're at line 8 and x is positive. If x is positive is one of our predicates. So now once we go and build a more refined abstraction, instead of checking whether we can get from here to one of the error states, we can change our property and just check whether the previously known error region is reachable instead. So this way, the model checker doesn't have to spend any time to recompute why error is reachable from here, and only has to concentrate on how can we make the analysis more conclusive for the part where it was inconclusive. So one interesting side effect of reusing previous results is that it also changes what counterexamples are available when we try to come up with a refinement. So typically, a model checker would use the shortest counterexample for refinement. So if we have these two counterexamples that both go to error states, a model checker would always pick this one. But if we were using our previous results, then maybe by the time we got to this abstraction, we're actually checking whether this error region is reachable. In which case, this counterexample would be the shortest one. And so this would allow us to guide the refinement towards the most promising counterexample. The counterexample that has the least number of steps until it gets to a point from which we already know that error is reachable. Finally, one other interesting thing about exact semantics is how they deal with imprecise abstraction. So typically, we would really like to use the most precise abstraction, but computing such a thing is very expensive. And so we have to live with some coarse abstractions instead. If we combine this with over-approximation, then even if an abstraction is coarse, it's still often sufficient to verify that error is unreachable. But refutation becomes harder because the coarser the abstraction, the more spurious counterexamples. But this is not really a problem for exact semantics. So here's an example. Here we have an abstract program, which is the best approximation of something. And it has the single execution, doesn't get to an error state, and so easy to show that error is unreachable. Now, if instead we use a coarser abstraction, maybe we decided not to compute what happens to be one here and here. Well, this coarser abstraction would introduce more behaviors in our over-approximation, but as long as none of these behaviors go to the error state, we can still prove that error is unreachable, and therefore verify that error is unreachable on the concrete program. But what happens if instead we have a program where error is actually reachable? So again, it's the same example, except now there's, this condition is negated, and so we can get to an error. Well, again, we have a single execution. It goes to an error state. Even in an over-approximation, we'll find it. It has to be a valid execution because it's the only execution of an abstract program. And we terminate saying we found error. But if our abstraction is not as precise, well, then this will introduce more behaviors. And the only way an over-approximating model checker can conclusively say that error is reachable, if it can find this black valid counterexample in this whole sea of gray spurious ones. So refutation becomes harder. And if we look now at what happens in exact semantics, well, if we make an abstraction coarser, we do get more transitions, we do get more possible transitions. But as long as there is enough information to prove that error is reachable, we'll have enough necessary transitions to do so. So here, for example, the reasoning would go as follows. It'd say, well, first of all, B2 becomes false. Then I get to this block of code, and I'm not sure whether I'm going to enter the if statement or not enter the if statement, but I do know whatever happens, B2 is unchanged. And therefore, by the time I get to this point, since B2 is false, this condition is true, and I'll get to an error state. So this abstraction is still enough to prove that error is in fact reachable. So to evaluate our model checker, we run it on several examples that come with Blast model checker, and compare the times of the two. Now, of course, YASM and Blast use very different heuristics, so just comparing times alone is not sufficient, but we wanted to have some kind of baseline to see what would be the acceptable performance of a software model checker on this example. And if you look at the times, well, YASM actually does fairly well. And one thing that may look surprising is that it needed quite a few more predicates for these two examples than what Blast used. And the reason is that since we found that exact semantics are not affected much by coarse abstraction, we found out that it's better to try and add lots of predicates during each refinement phase, but then do a very, very coarse abstraction, something which is computationally linear in the number of predicates. And then in many cases, this was sufficient to get a conclusive analysis, to get the conclusive result. So in summary, YASM is yet another software model checker. It's based on a combination of the CEGAR framework with reasoning over Belnap Kripke structures. The exact semantics of abstract programs that it uses enable more precise analysis, which is equally useful for true and false properties. And at the same time, it doesn't seem to add a significant computational overhead. And allows to reuse previous results and other extensions. The proof-based abstraction refinement that we use removes the requirement of having a linear finite CounterExample and enables checking of arbitrary CTL properties. If you're interested in more information on the tool, it's available on my webpage. So I started by giving you a list of some of my projects. I just wanted to kind of highlight the relationship between them. So really, multi-valued model checking is kind of en route of many of my other projects. So I showed you how it would be used in software model checking to reason about these partial models. It also can be used for vacuity detection, where we want to know how well is a property satisfied. And then these additional values that we can have in multi-valued model checking would keep track of which part of a formula is used where during the analysis. And it can also be used for temporal logic query checking, where we want to try and find propositional solutions to queries which are made up of temporal logic formulas. And in this case, again, the values would correspond to all possible solutions, to the lattice of propositional formulas. And what a multi-valued model checking would do is kind of compute with these values to come up with a solution to this query. So in terms of future work, well, in the long term, I plan to continue development and integration of automated reasoning tools for software engineering. In the short term, I'm interested in developing a more modular analysis framework, which is one of the limitations of existing software model checking approaches, since they are typically a whole program analysis approaches. But programs are not designed this way. They're designed modularly. And the only way we can scale the analysis to really large programs is to take advantage of this during the analysis. I'm also interested in looking at applying software model checking to concurrent systems. And one of the reasons is because our abstractions actually can tell the difference between non-determinism, which is due to concurrency, and non-determinism, which is due to something being unknown. And one of the problems there, so we can do fairly small examples of concurrent programs, but since we use control flow graph as our initial abstraction, it makes it hard to analyze concurrent programs since their control flow graph by itself is quite large. And finally, I'm interested in exploring new domains for automated reasoning. In particular, I'm interested in applying model checking technology to reason about security. And also, I'm interested in exploring analysis of web services, which on one hand are highly distributive and highly concurrent systems and have a fairly complicated communication primitive, which makes them rather hard to analyze. And on the other hand, it seems like in the future, most of the programs that we'll actually want to analyze would be some kind of web service. So finally, I want to acknowledge my advisor and some of the graduate students who worked with me on this project and some of the undergraduate students that I supervised during this time. And I think that's it.